Here we'll review the upper and lower bound theorems. Using synthetic division, we can show whether or not 4.5 is an upper bound. We'll begin by doing synthetic division by writing the 4.5 in the box on the left. This is what we'll be dividing by in our synthetic division. Then we place the coefficients of our polynomial at the top. We'll start by bringing down the 2 and writing that in the first position. Then we multiply the 2 times the 4.5. 2 times 4.5 gives 9, and then if we combine the negative 9 and positive 9, we'll get 0. Then we take that 0 also times the 4.5. 0 times 4.5 gives 0 again, and if we combine the 12 above with the 0, we'll get 12. Then we'll take the 12 times the 4.5. If we do that multiplication, we'll get 54, and 54 minus 9 gives 45. This 45 is our remainder. Since this remainder is not 0, this tells us 4.5 is not a root. However, to determine if it's an upper bound, we would like to see no sign changes in any of our 4 answers down at the bottom. You may note that all of these answers are positive except for the 0. However, when you're checking for an upper bound, 0 is safe. It is not considered a sign change. This means that 4.5 would be considered an upper bound here. And what that means is if we are trying to look for roots, we can remove 4.5, which is 9/2, from consideration. And we can also remove anything higher than that from consideration, meaning we have only 4 possible rational roots remaining. In a previous video, we removed all of our negative roots from consideration. However, I will show you how to check if one of them is a lower bound. If we were trying to determine if x equals -3 is a lower bound, we'll start by putting -3 inside of our box on the left, and once again write our coefficients above. We'll bring down the 2 as before, and now we'll multiply the 2 times that -3. 2 times -3 will give us -6. -9 minus 6 gives -15. Then we take that -15 and multiply again by -3. This will give us 45, but we'll combine that 45 with the 12, and we will get 57. Then we will take that 57 times the -3 one more time. This will give us -171, and if we combine that with the -9, we will get -180. Now to check for a lower bound, rather than looking for no sign changes, what we'll do is check for alternate signs for all of our terms. We can see our first answer is 2, that's positive. Our next answer is negative. Our next answer is positive. And our final answer is negative. So therefore, we have all sign changes. Since we have sign changes between every term, we will say, yes, this is indeed a lower bound. That means we can remove -3 from the list, and anything that is a bigger negative we can also remove from the list. Based on the results of this test, we would have only had 3 negative rational roots remaining. However, we said in a previous video that all of the negative rational roots were removed from consideration. So let's try this method again on -1/2 and see if we can remove all of the negative rational roots from consideration based on the outcome of that test. On this new slide, let's run this process with -1/2, written as a decimal, -0.5, as our divisor. We'll begin by placing the 2 by bringing it down to the bottom and multiply that times -0.5. When we do that multiplication, we'll get -1, and if we combine -9 minus 1, we'll get -10. Then we'll take that -10 and multiply once again by the -0.5. This will give us +5, and then 12 plus 5 will give us 17. Then we'll multiply that 17 times the -0.5, and if we do, we'll get -8.5. Combine that with the negative 9, and we'll get negative 17.5. So that we have a positive 2, a negative 10, a positive 17, and a negative 17.5. So once again, this will give us all sign changes. This means that negative 1/2 is indeed a lower bound, which means we can cross out anything more negative than negative 1/2. Therefore, negative 1/2 is removed from consideration, and all of the other remaining negative numbers are as well, which means we will have no negative rational roots remaining. We can remove them from consideration. Therefore, if we're looking for the roots of this polynomial, we no longer have to check any of the negative numbers, and we've proven that with the lower bound theorem.